Yes, right. So we will begin with current sources, but as I said, we will be finally concluding at differential amplifiers. Okay, with MOSFET loop. Okay. So we'll start with current sources. Right here, current sources. We know in any IC design, we definitely come across a lot of current sources, especially in analog IC designs. Whenever you are doing analog IC design, or whenever you are doing designing any what you say A to D converter or D to A converters, you will definitely have to use current sources. Okay, so the current source is very important. An example is shown you here. You can see a differential amplifier which we have studied earlier. It also needs to be biased with the current source. Okay, we have seen a lot of such example. For example, we have also seen what do you say, a common source amplifier with a current source load. Okay, where you have a current source connected there, right? So there are a lot of scenarios in analog IC design where you would be required to use current sources. You see this scenario here and this scenario here. And mostly our perception is whenever we want a current source, we can simply use a MOSFET. Okay, because it can act like a current source. Okay, how we can say that? Okay, so we know that a MOSFET, its current equation, if it is in saturation, its current will be 1 by 2 mu n COX W by L VGS minus VTH whole square. Okay, so we know that if we can bias it at some particular voltage, then this a MOSFET can behave like a current source. Okay, it can be behave like a current source. But the problem is, even though it behaves like a current source, the problem is it's a very, very bad current source. Okay, very, very bad current source. We will come to this point why it is a very, very bad current source. Okay, but before that, we have to understand that in order to make this current source, I need to bias this transistor. For example, you can see in this example which is shown here, in the differential amplifier where you require a current source, what you are doing is you are replacing this, you are implementing this current source using a MOSFET. Okay, and for in order to get your required current, whatever ISS is required, you need to apply the amount what you call sufficient bias voltage. Okay, so you need to give the appropriate bias voltage to it. Now the question is, how are you going to give the bias voltage? Okay, one of the solution is here. You can use a resistor bias network and bias this MOSFET here so that it behaves like a current source. Okay, so in this case, if you are using resistor bias, the voltage at this point is going to be VDD, voltage division rule, into R2 divided by R1 plus R2. Okay, so therefore the current I out produced by this device will be given by this equation. You can see this equation. So 1 by 2 mu 1 COX W by L, instead of VGS, because you have mentioned the bias voltage here, it is VDD into R2 by R1 plus R2 minus VTH whole square. So this is how you get the I out. This current source, whatever you generate, is a really, really bad current source. Okay, the reason why, okay, why it is a very bad current source. Okay, the reason for that is this current. What is a current source actually? What is a good current source? A good current source is the one whose what you say I out value, whatever is its current value, should be independent. First of all, it should be independent of its voltage, of its voltage across its end. Okay, V naught, and this current should be, okay, it needs to be independent. It should be independent of voltage across it, voltage across it. It should be independent of temperature. It should be independent of process variations. So if I want, let us say, if I'm designing current source of 1 milliampere, okay, no matter that means you where you implement this current source in an IC. For example, if this is my IC, and if I have designed the current source for 1 milliamperes, so if that current source is placed here in the IC, or whether it is placed here in the IC, or whether it is placed anywhere it is placed in the IC, it should give me 1 milliampere. Okay, which means So this is what is called as process independent, should be independent of the process. Generally, in a wafer, there is going to be lot of variations. Okay, so the parameters here, the mu and cox parameter, whatever you are having here, they will be, here you will be having a different value, here it will be a different value, here it will be a different value, because it's all based on chemical processes, and chemical process you cannot control to that degree such that you get or same mu and Cux value throughout the wafer. It is not possible. Okay, there will be some degree of variations. So, but due to that degree of variations, because you can see this I out is depending on mu and Cox, which means it is depending on process. This I out is depending on V naught. You can see it is R2 VDD into R2 by R1 plus R2. So if my VDD is fluctuating, let us say if I'm powering this IC with a voltage source with a battery, let us assume. So battery voltage is always not going to be constant. If it's a, let us say, 3.3 volt battery, so when I buy the battery at that time, it might be giving me 3.3 volt. But if I try to use it more and more, this voltage finally is going to drop because its strength is going to drop. So therefore, after some time, it will just give me 3 volts. Okay, after some duration. So therefore, this fluctuation in VDD, you can see, is reflected here also. That if VDD fluctuate, even this VGS voltage here fluctuate. And once it fluctuates, then it is depending on the voltage. So it is depending on the voltage. That means this VDD. It is depending on process. It is depending on temperature also. High temperature, because these two contradicts mu and is dependent on the temperature. So if mu n is dependent on the temperature and VTH threshold voltage to some extent is dependent on the temperature. Okay, so because of that, it is going to vary with temperature. If temperature is going to vary, even this current is also going to vary. If you design for 1 milliamperes, it might be generating 1.1 milliamperes after some. If the temperature increases, you might have designed at 0 degree Kelvin. Sorry, that means 0 degree centigrade. But actually using it at 40 degrees centigrade. So you may have different current because it is dependent on temperature. Why? Because this parameter mu1 is temperature related. This VTH also is temperature related. Right. Now, not only that, okay, so it is varying because of process, it is varying due to process, it is varying due to VDD, it is due voltage across the terminal. This MOSFET, you can see the here, we have just drawn an open-ended signal. But generally, you will have a voltage. You need to connect some voltage source or you need to connect some load here. So the moment we connect the voltage or load here, this voltage, okay, which we call it as VDS, which is between here and here, VDS voltage, again becomes, what do you say, undefined. So once this voltage source is undefined, this voltage across the drain is undefined, okay, is different, this is going to vary because this equation, whatever I have written here, this equation is written assuming there is no channel length modulation. But in practice, there is going to be a channel length modulation. You will be having 1 plus lambda into VDS. Okay, so therefore, if this load, this drain and source voltage is going to vary, then the I out is also going to vary. So therefore, now you can see I out is not independent. Whatever current source you have designed, actually, if it's a very good current source, it should produce same current irrespective of any changes in any parameter. But you can see your current is depending on process, your current is depending on VDS, your current is depending on the battery which you are using, it is depending on the temperature, okay, and a lot of different variations. So therefore, the current source which is produced here is not a good current source. Okay, it is not a good current source, not a good current source. Okay, why? Because it depends on all this value. We don't want it to depend on all this value. So therefore, in IC, what we do is wherever we require current, here you can see here we require a current source. Instead of designing current source by using a MOSFET and then designing it W/L ratio and something like that, instead of this, what we do is we take a golden current source, a golden or a pure current source, which is, what do you say, very ideal, which is irrespective, which doesn't vary with temperature, a golden reference. You can call it as a golden reference. So we will take a golden reference, which is designed in a very, very complex way. It is not just a MOSFET and you're connecting it with some bias voltage. Not like that. It is designed very in a very complex way. And how it is designed, we are not going to discuss. It is not part of our syllabus. Okay. But anyways, if you want, I can talk about that some other point of time. But it is designed in a very complex way. Okay, mind you, you will be using at least, if not 15, more than 15 transistors, you will be using to just design this current source. So that in order to make it independent of process, independent of VDS, independent of VDD, independent of temperature, and all those things. So what we will do is we'll spend a lot of time and we will design one golden reference. Okay, and whenever you want to bias any current source, whenever you need this, you need to bias any circuitry using a current source, what we will do is we will copy this current to uh, using our MOSFET. Okay, we will copy the current, whatever is produced here, into wherever you require it. So we just use a copy circuit. So we, in other words, what I'm trying to say is we design a single current source for an entire IC. We will design a reference, golden reference, and it requires a lot of effort. By putting a lot of effort, you will design a golden reference. And wherever this reference is required, you will just copy it. So wherever any circuit is requiring that, for example, in the differential amplifier, just now we have seen it was requiring a voltage, a current source. So what we will do is we'll simply copy this current here, and instead of placing a current source there, we will simply copy this current here. Okay, and it behaves like as if this real reference is present here. And in the other amplifier, let us say if I have another circuitry, just now we have seen common source amplifier with current source load. So for this circuit also, instead of placing a current source there, what we will do is we will use a copy circuit. We will simply copy the ideal current source, ideal current from here to here, and then use it. Okay. The reason why we are using copy circuit instead of designing this current source itself is, instead of designing current source, replacing this with an ideal current source. Why we are using copy circuit is, the reason is designing this reference is very, very difficult. You cannot design it each and every place because it is going to be very bulky also. But whereas designing copy circuit is going to be very easy. You can easily design copy circuits. So therefore, we design one golden reference and we copy the same current wherever it is required by using some copy circuits. Okay, so how can you copy this current? Okay, so in order to copy this current, we use what are called as current mirrors. So there comes the current mirrors. So current mirrors are used to copy the current. Okay, and how do they copy? They copy like this. Okay, so you have a golden reference. Okay, and what we will do is we'll simply place a transistor like this and another transistor like this. Okay, and here this is the golden reference current that is flowing, I ref, and in this way the I out will be equal to I ref. Okay, so this circuit which I have used here, this circuit which I have used here is called as current mirror or copying circuit, current copying circuit. Current copy circuit, which is usually we don't call it as current copy circuit generally in literature. We call them as current mirrors. Now let us understand how do they mirror. Okay, how do they mirror? Okay, so we know, let us say in this, with this equation, let us commit this equation. This is normal equation. If I write about current source neglecting channel length modulation, it is 1 by 2 mu n COX W by L VGS minus VTH whole square. In other words, ID is a function of VGS. Okay, or I can also write it as VGS can be derived as an inverse function of ID. Okay, so which means if I have a current source, IREF, okay, and this IREF, if I make it flow through this particular circuitry like this, okay, in order to make the VGS dependent on IREF, you have to short the drain and source, because we know when the current flows, VDS changes. Okay, and if you want VGS also to change, you can simply short the gate and drain. Okay, so in this way, changes in the VDS will also reflect in the VGS. Okay, so this is the VGS. Okay, and how we'll give this VGS? This VGS is given as an inverse function of IREF. Whatever VGS you get here, that is actually decided by, that is actually depends on how much current is flowing. If you flow 1 milliampere, you will get a different VGS. 2 milliampere for different VGS. Okay, why we need to short this is why we need to short drain and sources. When you short drain and source, your VDS will be equal to VGS. Okay, first of all, why we need to short this drain and sources? Because this current, whatever we are talking about, the f of VGS, we have derived it from this equation. And this equation is the equation of what is this equation? It is equation of what? Are you listening?
Current, sir.
Equation of which current?
Saturation.
In
Drain
saturation.
current. Okay.
It is equation of drain current in saturation. Okay, so that means whatever discussion we have done here, that is valid only if you assume the transistor is in saturation. And when will be the transistor in saturation? What is the condition? VDS should be greater than or equal to VGS minus VTH. This is the condition that needs to be satisfied. And once you connect the drain and source, okay, your VDS will be equal to VGS. Okay. So once it is equal to VGS, we know always as per this condition, what is your VDS? VDS now is VGS. It is greater than or equal to VGS minus VTH. It is obvious, right? Let us say if you have VGS is equal to 1 volt and VTH is equal to 0.5. So you have 1 greater than 1 minus 0.5, which is 1 greater than 0.5. Is it true or not? Is it true or not?
Yes, sir.
So by shorting drain and gate, what you are actually doing is you are making sure that the transistor is always in saturation. Okay, so you can put any value of VGS here, any values here except less than threshold values, except for you should not go below threshold. For any value greater than the threshold voltage, this transistor will be in saturation. Okay, so that is the reason why we have shorted this. So this circuit, this short will make sure that it is always in saturation. And once it is in saturation, this condition applies. Its VGS will be simply inverse function of its IREF. Now, if I want to recreate another circuit, let us say I have connected another transistor. Yeah. Now let us assume here I connect another transistor like this, and if I try to see what is the current flowing out from this, what will be its I out, because it's again a transistor. Okay, and you are applying it the VGS, whatever is applied here. So therefore, this is in saturation. Obviously, this will also go into saturation. So this I out will now be given by, just now we have seen, I out or ID of any transistor is a function of its VGS. So which means this I out will be equal to f of its VGS. And if this transistor is M1 and if this transistor is M2, let me call this as VGS2. And this VGS, the difference between here and here, I call it as VGS1. Okay, so from the figure you can see the node where VGS2 is present, the gate node of 1, transistor 1 is connected to gate node of 2. So in other words, VGS1 is equal to VGS2. Okay. So therefore, the I out here was actually, if I write it here, I will write it here again. I out here was equal to F of VGS of this transistor. This transistor is 2, VGS of 2. But we know from the circuit, because both the sources are grounded and both the gates are connected to the same point, VGS1 equal to VGS2. So therefore, yes, you can replace it VGS2 with VGS1. Again, what was this VGS1? Okay, this is VGS1. What was this VGS1? VGS1 was given by this equation, F inverse of I ref. So this is F of F inverse of I reference. Okay, so you are having F of F inverse, which is going to cancel each other, and that means which is going to result in just this variable which is present here, which is I ref. So you get your I out equal to I ref. So this is how the current mirror circuits copy. So they copy based on this what do you say, logic. However, this discussion, whatever we have done, is valid only if the dimension of M2 is equal to dimension of M1. It is valid only when their dimensions match. Okay. The reason why I'm saying that, let us just see in the next slide. Just remove this. Yeah. Why dimensions are very important is because just now, if I just repeat the figure, you were having I ref, the golden reference, okay, and then you were copying it using MOSFET. So this I out, whatever you were getting, it was function of VGS2, which was again equal to VGS1, because VGS1 equal to VGS2, but VGS1 is nothing but it is inverse of I ref. So you were getting I out equal to I ref. Okay. In other words, if their currents are same, what does it mean? What is the equation of current through this transistor? Let me call this as M1, this is M2. So current through M1, ID1 is 1 by 2 mu n COX W by L VGS1 minus VTH1. Okay, so ID2 will now be 1 by 2 mu n COX W by L. This is W by L of first transistor. This is W by L of second transistor into VGS2 minus VTH2. Okay, so as per this equation, if I out needs to be equal to I reference, which means ID1, if it has to be equal to ID2, then their equation 1 by 2 mu and COX W by L VG W by L of first one into VGS1 minus VTH1 should be equal to 1 by 2 mu n COX W by L VGS2 minus VTH2. Okay, so for these two currents should be same. What is that you should say? Let us say if they are manufactured on same wafer, first of all, they should be on same wafer. Okay, so if they are on same wafer and at almost the same location, then you will have mu n same and COX same. So once mu1 and COX are same, 1 by 2 anyway is same, you can cancel it out. Mu1 COX becomes same, you can just ignore that. Then their threshold voltage should be same. Okay, so if their threshold voltage should be same, what does it mean? It means that their length should be same. They should be of same length and on definitely on same wafer. That is already we have discussed. So if they are on same wafer and same length, then you can have VTH1 equal to VTH2. Okay, so then these two becomes same, and their VGS1 and VGS2 anyway is same because they are shorted to the same node. Okay, they are connected to the same node. So VGS1 and VGS2 anyway is same. So if you can just make sure that their lengths are same, then the threshold voltage also will be same, and this can be ignored. This you can cancel. Okay, ultimately, for now the current to be same, only one condition that you need to satisfy is W by L of first transistor is equal to W by L of second transistor. In other words, W by L of 1 should be equal to W by L of. Okay, so these conditions you need to satisfy in order to build a proper current mirror. What are those conditions? First of all, they should be on same wafer. They should be on same wafer. Okay, they should be of same length, and their W by L ratios, because their length is anyway same, you can also say that width 1 should be equal to width 2. In other words, instead of equating them, let us say if I try to write the equation of I out by I reference, then I will be getting this by this. You will be having 1 by 2 mu n COX W by L of first transistor into VGS1 minus VTH1. So this is I naught. So I naught is for second transistor. So you have W by L of 2 VGS2. Okay, VTH2. And what is the I ref equation? Mu n COX. Because I naught is nothing but second transistor ID2. I1 is nothing but first transistor ID1. Okay, so their equation I have substituted. So this is what we get: W by L of 1 VGS1 minus VTH1. Again, if you satisfy all the three conditions that they are on the same wafer, almost close to each other, they're of same length, then you can cancel out all those things here. All these things gets cancelled out, and you will be only getting I out by I reference, I out by I ref is equal to W by L of second transistor by W by L of first transistor. So the ratio of current depends on the width. This is the property under your control. Remaining things you cannot control because they are fabrication dependent. This thing is under here. Okay. So this also means one more thing. Okay, what does it mean? It means that I can not only copy the same current, I can also derive another currents from my I reference. For example, I can get an I naught, which is equal to I ref times, if I just cross multiply, you have W by L of 2 by W by L of 1. Okay, so let us say if I given the I reference to me is equal to 1 milli, or let us say 100 microamperes, but I want a current which is 250 microamperes. Okay, so how will I get that? How can I get an output current of 250 microamperes? I have to simply maintain the ratio. Okay, so this equation I can write it as I naught is equal to I ref into some alpha, where alpha is simply the ratio of W by L of second transistor to W by L of first transistor. Okay, so if I want 250 milliamperes, but my golden reference is of just 100 microamperes, but I want 250 microamperes, then what I can do is I can choose W by L of second transistor to be equal to 2.5 times W by L of first transistor. So I will choose W by L of first transistor equal to 1, whereas W by L of second transistor equal to 2.5. So when I use this, then this ratio turns out to be, this ratio I will get it as W by 2 by 2.5 by 1, I will get it as 2.5. So therefore my I naught will be 2.5 times my I reference, which is 100 microamperes, which ultimately gives me 250 microamperes. Okay, in other words, what we are trying to say is, with a single reference, with a single golden reference, you can derive any current whatever you want just by choosing appropriate ratios of M1 and M2 transistors here in this current mirror. Okay, so your copy current circuit can not only copy the same current, it can also scale the current and copy it. You can scale the current and copy it wherever you want. So that is what is the current mirror. Is it understood?
Yes, sir.
Yes, sir.
Now there is a problem with the current mirror, whatever we have discussed. Okay, obviously. What is the problem? Because in all the discussion, whatever we have done so far, we have ignored the channel length modulation. Okay, so if you consider channel length modulation, if I consider channel length modulation also, then their ID1 and ID2 equation will not be mu1 cux w by l vgs minus vts whole square, but also it will include one more term which is 1 plus lambda vds1. Okay, so if you include channel length modulation, then the ratio of the current ID2 by ID1 will not be just W2 by W1 as we have seen in previous class. I have simply previous sheet. I have simply said I naught is just I ref into. I said that I naught is simply I reference to W by L of 2 by W by L of 1. Okay, but in practice, if you consider channel length modulation, so I naught by I2 will be W by L of 2 by W by L of 1. No doubt it will be there, but along with that, 1 plus lambda into VDS by 2 by 1 plus lambda into VDS 1. This also becomes part of the ratio. Okay, so now this is your ratio. Now the second current or ID2 or I out, you can call it as, will now be equal to ID1 into W by L of 2 by W by L of 1 into 1 plus lambda VDS2 by 1 plus lambda VDS1. W by L of 2 and W by L of 1 is under your control. It is completely under your control. And you can design it, whatever value you want, you can give it. But the problem is VDS1. Okay. What is VDS1? VDS1 is, you can see, drain to source voltage of this transistor, VDS1. And what is VDS2? VDS2 is the drain to source voltage of this transistor. Okay, let me draw it here. Let me draw it here again. Okay, so this is your VDS1 plus minus, this is VDS1. Okay, here you have plus minus VDS2. Okay, so the problem is I can maintain W by L ratios constant, that is under my control. I can design it appropriately. But when you come to VDS1, here you can see VDS1 is well defined. Just now in the previous discussion also we have seen this V drain is connected to gate. So therefore VDS1 is nothing but it is equal to VGS1. Okay, and what will be VGS1? VGS1 will depend on this I ref. Okay, it will depend on the I ref, you know the condition. Okay, what will be VDS1? It will be 2 times ID by mu n cox w by L under root plus VDH. This will be VGS1. Okay, this equation we have written it earlier also, but you can also derive it. It's not a very big deal. Okay, you can simply take this equation. You can take this equation, cross multiply, 2 goes that side, divided by mu n cox, a square root of that plus VTH. Okay, plus VTH. That is what is going to be. So which means VDS1 is known to you. I can know VDS1, and that is directly dependent on ID. I can choose appropriate ID and know what is VDS1. The question is, what is VDS2? What is VDS2? Here, because you know VGS1, you know VGS2, because VGS1 here is connected to VGS2. So knowing VGS1 will give you a chance to know VGS2, but you don't know what is VDS2. That is the biggest problem. In current mirror, the drain to source voltage of second transistor is not under your control. Who is going to control that? That is completely going to depend on whatever is the load connected to this, or whatever is the circuit connected to this. You may have any circuit connected to it, as we have seen. Okay, so here there can be a differential amplifier connected to it like this, or you can have a like this. You can see a MOSFET connected to it. So we don't know what is connected to it, and that is going to decide what is connected to that is going to decide the VDS here. So unless and until we know what is connected here, we cannot decide. And it is not possible for us to study the current mirrors on case by case basis. We have to generalize the case. Okay. So because we cannot define the VDS of second transistor, we will not be able to know this VDS2. The moment we don't know this VDS2, you don't know what is going to be the ID2. So therefore, ID2 will be some, okay, it will be ID1 plus some error, which is mostly because of VDS2. Okay, and it can be huge. It can be huge also. Let us say if you are designing the circuit for 1 milliamperes, if you want ID2 to be 1 milliampere, okay, when you design it, you should not be shocked if you get an current of 0.2 milliamperes, okay, because this ratio is completely depending on VDS. So based on VDS, it can go to anywhere. It can also become zero. Okay, right. Now, what is the solution to this? What is the solution? Okay, how to make this second current independent of VDS2. We want to make it independent of VDS2, because if it becomes independent of VDS2, if we can just omit this ratio, we will be we will be having our old equation, which is ID2 by ID1 is equal to W by L of 2 by W by L of 1. So therefore our designing will be very, very easy, or we will be able to copy exact current whatever we desire. Okay, so we have to get rid of this ratio. How are you going to get rid of that ratio? The solution to that is yeah, I need to add some extra papers here. Yeah. Yeah. So what is the solution? How can I get rid of this ratio? The solution to that is you use this circuit. Okay. You use cascade current mirrors. Okay. So how will the cascade current mirror look like? The cascade current mirror will be like this. Okay. So you have a current source here, first transistor, and the other transistor you have it here. And cascade means you use another transistor here, okay, in common gate configuration. I misconnected it to some bias voltage VB. So in this case, whatever I out you are going to get, this is going to be equal to your IREF. Actually speaking, it is not going to be an ad hoc. You simply take the circuit, put some values of W by L, you are not going to get. It requires a careful design. Okay, so what should be the careful design? Okay, the careful design is we want this VDS. What is our problem? The problem is with VDS1. We know VDS1. We have to make VDS2 equal to VDS1. This VDS2. Why we want to make VDS2 equal to VDS1? Because if this VDS2 is made equal to VDS1, then we can simply strike off this term and we'll be getting our golden equation or a good equation. Our what do you say, favorite equation, I W by L of 2 by W by L. So we need to make VDS2 equal to VDS1. Okay. Why? Is because we want to get rid of this ratio. Okay. So now that is what is our intention. We want to make VDS1 equal to VDS2. How are you going to do that? Is we know for this transistor M3 to be in saturation, okay, for this transistor M3, the voltage at its source end, okay, and what do you say, the difference between its gate and source, okay, so that is VGS of 3 should be equal to, is nothing but VB minus, let this point be Y, let this point be X, okay, so it is VB minus VY. Okay, right? Or in other words, your VB is equal to VGS3 plus VY. Okay, and what is your Vx? Your Vx, we know here, this Vx, this voltage is nothing but it is the gate to source voltage of first transistor VGS1, and it is also the gate to source voltage of second transistor VGS2. So Vx is nothing but it is equal to VGS1 and it is equal to VGS2 also. Our intention is to make VDS1 equal to VDS2. In other words, we are naming this node as X and this node as Y. So our intention is Vx should be equal to Vy. Or in other words, that means VDS, our intention is VDS1 equal to VDS2. In other words, Vx, voltage at node X, should be equal to voltage at node Y. Okay. So if you want node X voltage to be equal to node Y, from this equation, I can get node Y voltage as Vy is equal to Vb minus VGS3. Okay. And for them to be in saturation, these two should be made equal. So that means your Vx voltage, if I want Vx to be equal to Vy, just substitute Vx here, Vb minus VGS3. Or in other words, your bias voltage should be equal to Vx plus VGS3. Okay, what is Vx? Vx, we have just now seen that Vx is nothing but it is the voltage between first transistor VGS1. In other words, your Vb should be equal to VGS1 plus VGS3. This needs to be satisfied. Okay, so this transistor, your Vy, the node Y voltage will be equal to node X voltage if bias voltage here is chosen such that this bias voltage is equal to VGS1 plus VGS3. Okay, so if you can take this, if you can achieve this condition, okay, then the VDS here becomes VDS2 here. So therefore, you will be able to cancel this channel length modulation effect, and you'll be getting only ID2 by ID1 equal to W by L of 2 by W by L of 1. Okay. Now the question is getting this VB, calculating this VB, and again using a resistor bias to get this value is very difficult. So we need to look for ways to automatically generate this VB. Okay, so this VB can be automatically generated if you use this circuit. Okay, how to automatically generate VB. Okay, so you can use this circuit. Okay, let this transistor be the same M1 transistor. I'm just drawing this. I have made changes to this what do you say, path. So that path changes I have made. I have added one more transistor M0. Okay, so this was our old node X. Okay, and let me call this as node N. Okay, so what is the voltage at node N? Voltage at node N, you can see this voltage is equal to the voltage at this end, which is Vx, plus the VGS of this particular transistor, VGS naught. Okay, so it is Vx plus VGS naught. So this N voltage is Vx plus VGS naught. Okay, now if I on the right, if I take this circuitry and connect it here, to the same old configuration which we have drawn here in this figure, I'm coming back to this configuration. Instead of connecting VB to M3 transistor, I am connecting the node N to M3 transistor. Okay, So this is your M1 transistor, M0 transistor, M2 and M3 transistor. Okay. So now for M3 transistor, because it is connected to node N, what will be the voltage at this Y? Okay, the voltage at Y, that is Vy, will be equal to Vn, this voltage, minus VGS3, plus minus its gate to source voltage VGS3. Okay, what is Vn? We know from this equation Vn is there. So if I bring that and substitute here, so your Vy will be Vx plus VGS naught minus VGS3. Okay, so if you can choose appropriate values for M0 and M3 transistors, if dimension of M0 and M3 are chosen appropriately, then you can make VGS naught equal to VGS3. And if VGS naught becomes equal to VGS3, from this equation you can strike it off. You will get Vy equal to Vx. Okay. So why this dimension has come into picture? The dimension has come into picture based on previous equation. Just now I have said you the equation, right? VGS value is going to be under root of 2ID by mu n COX W by L plus VTH. Okay, because the same current is flowing in this circuit, and this circuit. So both their IDs will be same. You will get the same ID. The process is same, so therefore they will. If you maintain their length same, their threshold voltage also will be same. So this you will make, this will become same, this will become same, and yeah, they are on same wafer, so mu and CX will be same. So ultimately, if you want the complete thing to be same, the only thing which is remaining is W by L. So you have to choose W by L of these two transistors, that is M0 and M3, to be same. So if they are same, you will get this. Vx equal to Vy. In other words, what is Vx? Vx is nothing but it is a voltage, VDS voltage of first transistor. Vy is nothing but VDS voltage of second transistor. So you have made VDS1 equal to VDS2. So therefore, the current equation, which was ID2 by ID1, is equal to W by L of 2 by W by L of 1 into 1 plus lambda into VDS2 by 1 VDS2 by 1 plus lambda into VDS1. VDS1 and VGS2 both become same. You can cancel them. So ultimately, this is going to be the resulting equation. Okay, so that is what is cascade current mirror. So you can go and use this current mirror and solve your problems. Okay. So in this way, you will be able to perfectly copy this current. One more advantage which you will get with this current mirror is this current mirror. One more advantage is it is going to protect or shield. It is going to shield M2 from variation in VP. Let us say if this node you are calling it as VP, this node is VP. Earlier in the circuit, we have seen in the earlier, figure, that this VDS you cannot control because that was under the control of some load device. Okay. So there is going to be some load device and that is going to decide the voltage at this end. Okay. So if this end voltage you are calling it as VP. Okay. So if there are any changes in VP, at this end, VP here, VP here for this circuit here, then that changes will not be causing much changes here at Vy. Okay. So any change in VP will not be translated to Vy. Any change in VP will not go to Vy. How can I say that any change in VP doesn't go to Vy? The reason why I'm able to say that is because if you see this transistor, it's a common gate transistor. And for a common gate transistor, its voltage gain is 1 plus Gm in R0 whole divided by Rs plus R0. Okay. In other words, its gain is a high value. Okay, so its gain is high. Okay, if its gain is high, What does it mean? What is gain? Voltage gain is nothing but V naught by Vi. It is very, very high. Okay. Or in other words, V naught is some high value into Vi. Okay. If I write it in reverse way, its input is V naught divided by high. Okay. 1 by high is going to be very, very low value. Okay. So your Vi will be V naught into low. Okay. In other words, for a common gate, what is the input and what is the output? This is the input for the common gate and this is the output for the common gate. So if there are large voltage variations in Vp, that large voltage variation will be multiplied by a very low value. Okay, which means the resultant variation at input is going to be very, very small. Okay, so that is why you say that this this cascode current mirror is going to shield this device from variations in this Vp voltage, and because of that, this transistor will be what do you say, producing exactly the same current. Right. So anyway, wherever you have an advantage, you will have what do you say, its own disadvantage. So the problem with this current mirror is you have to design it very carefully. Okay, not only you have to design carefully. Okay, it eats away some voltage from you. That means your output cannot go to zero here. Okay, why your output cannot go to zero is because you have to maintain these two transistors in saturation. Okay, so when these two transistors are in saturation, that means there should be some minimum voltage. I will talk here. Let me use a different color. Okay, it means there needs to be some minimum voltage that needs to be maintained here. Okay, some V minimum that needs to be maintained here, below which you cannot go. So your Vp should always remain greater than this particular value. It cannot go less than this value. What is the least value you can expect here? The least value is you want this transistor to be in saturation and this transistor to be in saturation. When they are in saturation, they consume what is called as overdrive voltage, VD sat. So you have VD sat 2 and here you have VD sat 3. So the minimum voltage, Vp minimum, whatever you can have in that circuitry, is Vd is equal to the saturation voltage of second transistor plus saturation voltage of third transistor. You cannot go, let us say if the saturation voltage of second transistor is 0.2 and third transistor is 0.3, then the minimum value which Vp can take is 0.2 plus 0.3. Okay, 0.3, which is 0.5. It cannot go, the swing here at this point cannot go below 0.5. That means you will not be able to go to 0 volts. That is the problem. Okay, it eats away some voltage from the range from 0 to 3.3 range, whatever you are having. From that 0.5, you have to leave away for these transistors to work, and remaining you can use. That was cascode current mirror. Let us now move on to the next topic, which is active current mirrors. In the cascode current mirror, there is another category which is called as low voltage cascode current mirror. Okay, in low voltage cascode current mirror, what we do is we use the cascode. We use cascode. What do you say? Setup. Let us say in the output. But here, what we do is we connect the drain of this transistor to source of this transistor. Okay, like this type of setup we use. The advantage of this setup is it actually requires an overdrive voltage. The overdrive voltage which is present from here to here, that voltage will be equal to just VDS1. Okay, VDSAT1. And VDSAT1 is a very low value. So you can have VDSAT1 equal to 0.1 also. You can design it. So therefore, you will be having maximum swing. So this is a cascode current mirror with what do you say, low voltage. It is not there in the syllabus, so I'm skipping it. So if you would like to read it, you can go and just read this transistor. But designing this circuit is quite complex because there are some 2 to 3 conditions that needs to be met for this circuit to work, or else this circuit will not work. Okay, so that is the only problem. Now, the cascode current mirrors, they can not only copy current. We have just now seen that they copy current. Okay, like in differential amplifier, wherever you want to bias. Okay, so they copy the current and you can bias it. Okay, so they are not only used for biasing purpose. Current mirrors current mirrors are not only used for biasing, they are also used for amplifications, for signal amplification. And if you are using current mirrors for amplification purpose, that is to amplify signals, then you call those current mirrors as active current mirrors. The current mirrors which are used for biasing purposes, you call them as passive current mirrors. Okay, so just now current mirrors, whatever we have seen, the normal current mirror, simple current mirror, and cascade current mirror, they come under the category of passive current mirror because they are usually used for biasing purpose. Similarly, you can also use current mirrors for amplification purpose. Okay, how can we amplify the signal using current mirrors? You can see here. If I take this current mirror here, okay, if there is a signal, let us say it is biased here. To this input, if there is, let us say, some change, delta I change, if it occurs here, then your I out will also be I in plus delta I. It will also become I in plus delta I. For example, if you have chosen the width of W by L ratio of M1 to be equal to 1 and W by L ratio of M2 equal to 10, then this becomes I in into delta I times 10. Okay, so this 10 into I in, you can treat it as a bias voltage, bias current, plus the small change multiplied by 10 is what is the amplification. And so it is the small change I said you was the signal. So that signal, whatever you are giving here, it is actually becoming amplified. So obviously, apart from the signal, you are having some DC. We know how to get rid of the DC. So DC is not a big problem. So you can leave it aside. So small signal is getting amplified. So this is how what do you say, a current mirror can be used for amplification. The only thing here is you should apply current inputs for getting amplified current outputs. Okay. There are scenarios where instead of applying current inputs, you can apply voltage inputs also. But this circuit ultimately will give you voltage amplification. That means it does voltage to current conversion, amplifies current, and then multiplies with the resistor to give you voltage back. You will get an amplifier. An example of that circuit is shown here. Okay, so this is a circuit where this current mirror circuit is used. Okay, but it is actually acting like a what do you say? It is participating in the circuitry to amplify the signal. It is used for signal amplification purpose. Now let us try to analyze this circuitry. It's a normal what do you say, differential amplifier. You can see M1 and M2 are forming differential pair, and you're connecting the input signal here. Okay, so that means this end is Vi plus, this end is Vi minus. You can see in the first branch there is no resistor. Okay, so there is no resistor here. We are not dropping any voltage or anything like that. In the second branch there is no resistor, but instead there is a current mirror. Okay, so what we will do here is we will use this current mirror as current source. You remember this circuitry which we have used in current source amplifiers. You have current common source amplifier. So you have common source amplifier with current source load. So if you remember the circuitry, you know this circuit actually acts like an amplifier with a gain of Gm into R0. Okay, so here this source is actually helping you by providing a large output resistance which you can use to amplify your signal. So same is the case here. So the current mirror used here is helping you to amplify the signal by providing high output impedance. So instead of using this current source, we know how we generate. Just now I have discussed a lot in discussion we had it. So we cannot just put a current source, but it is easy to put a current mirror. So therefore we have replaced this current source with a current mirror, and that current mirror is getting its current from the golden reference. This I1 is a golden reference. Right. So it is as if this circuit is having on one end directly connected to VDD, on the other end it is connected to a current source. It is as if we are working with this circuit. Is it okay? Okay. So this circuit ultimately can be simplified to like this. So instead of current source, as I just now said, we don't use current source because generating good current source is very difficult job. So we use current copy circuit. Current mirror is used instead of that. Now, Now, for this circuitry, what is going to be its output gain of this particular circuitry? What gain you will be getting here? Let us just analyze that circuitry. Okay. So for analysis, we know the gain of the any circuitry voltage gain. You can find it by getting its GM and multiplying it with R out. Okay, a large signal GM and large signal R out here. We are not going to place any small signal model here. Okay, if it's a small signal GM, I would have written like this. GM is large signal GM. That means we are not going to replace with model directly from the analytically. We will finding it out here. Okay, so this is the circuit which is used for GM calculation. So you can see in order to calculate GM, what you have to do is you have to short the output. So output is shorted. So there is an I out flowing here. Okay, so the I out which is flowing here, actually the direction is here, but it is going to flow in this way. Okay, because the VDD is on the top, so current is going to come in this way. Okay, so how much current will be going to come from there? Okay, so we know that half of the V in from here, so V in by 2 will be applied here, plus and minus V in will be applied here. Half circuit, you know, this circuit can be split into half circuit mode. So this V in by 2 current will be flowing here. The remaining V in by 2 current will be flowing here. Okay, so therefore the I out here on this branch is going to be GM. Okay, GM is nothing but the GM of this transistor. So you have GM into V in by 2. And it is going to be negative in this branch. It will be positive in this branch. But we are not bothered about this branch because we want GM. The load is connected here in this branch. And you know, as per our earlier analysis, we can actually split this. So this will be a separate node, separate circuit. This will be a separate circuit. We are not bothered about this circuit because there is no output taken from this circuit, left hand side, but there is output taken from the right hand side. So therefore, this circuit now can be drawn like this. So you have an I out, and here is this transistor who is having a GM. You're actually applying a signal V in by 2. You can assume it like this when you're doing half circuit analysis. Okay, so when you apply V in by 2, the output current what you will be getting through this circuit is GM, which is GM of this transistor into V in by 2 in negative way. Okay, because it's a inverting way. Okay, so therefore I out is minus GM V in by 2, which means your GM, what is GM? It is a output current by input voltage. It is going to be minus GM by 2. So this is the GM of this complete circuit. So complete circuit GM, large signal GM is going to be small GM by 2. Now let us try to find it R out. So in order to find out R out, what you can do is, because you are applying signal here, this transistor I will take. Okay, this is anyway open circuited, you can just ignore that. So when you see it from this side, okay, so you will have a transistor here, and when you're seeing from this side, assuming that it is grounded, and you see from source side, it will give you an impedance of 1 by GM, and that is now connected to VDD. VDD, as per our analysis, should be shorted, so it will be connected to ground. So that is what is the diagram drawn here. So you are seeing from this side, you are having input connected here, this transistor. The other transistor is replaced by simply a resistor whose value is 1 by GM, and its VDD, it was connected to VDD, so we have grounded it here. So output resistance is simply the resistance when you see it from this side. If you remember, if you recall this circuitry, if you just imagine this circuit is actually looking as the circuit with common source amplifier with source degenerate resistor. Okay, so you have RS, you have V in, this is your V out. This is CS amplifier with source degeneration. And for CS amplifier with source degeneration, its output impedance R out. That means ignoring this, just R out if I calculate from this side. So its R out will be given by, what is the equation? 1 plus GM into RO1 times RS plus RO1. So this is how, this is going to be the impedance seen from this side. Okay. So when I substitute it here, what is that you will be getting? You will be getting 1 plus GM1 into R1. Instead of RS, what is that we have here? We have 1 by GM1. 1 by GM1 plus R1. So when you multiply this, what you will be getting? You will be getting 1 by GM1. Second term, you will be getting just R1, GM1 will cancel, and another one more R1 you will get. So what you will get is 2 R1 into 1 by GM1. So not into, plus 1 by GM1. And I have said you many times that R1 value will be in kilos of ohm, where hundreds of kilo ohm. GM will be small, 1 by GM is going to be small. So R1 is very much greater than 1 by GM. So therefore, this can be, R out can be, what do you say, approximated as 2 into R1. Okay. So 2 into R1 is just the resistance from this side, looking this side. Again, from this side and VDD, you have R02. So therefore, from output node to ground, you are having a resistance of 2 R01, which we have just now found out. Okay, again from that output node to VDD again you can replace it as small signal ground. Its resistance is R04. So the total R out for this circuitry is equal to parallel combination of R04 and 2 R01. Okay, so this is what is R out. Okay, so we have GM, which we have calculated earlier, which is minus GM1 by 2, and we have R out, which is here. So therefore, the voltage gain of this circuitry is simply, its voltage gain is capital GM into R out. So GM we got it as minus GM1 by 2, R out we got it as RO4 in parallel with 2 RO1. If RO4 is very large, assume, just assumption, RO4 is very much larger than RO1, then you have simply GM1 by 2, and this is equal to very large, that is RO4 is almost equal to infinity if we assume, then you will get into 2 RO1, 2 gets cancelled, so you will get minus GM1 RO1. So this is the gain of the circuit which we have seen here. Okay, so in this way, the active current mirrors can help you amplify the signal, okay, by providing high output impedance. So M4 was providing a very high output impedance, and with the help of that, we'll be able to get a good gain. Right. These active current mirrors are usually used here in differential amplifiers. Okay, so differential amplifiers, what we will do is, see here, the problem with this circuitry is, why only this circuitry we have chosen? For example, I could have chosen any circuitry for the exam, for saying that current mirrors how can amplify. The reason for choosing this circuitry is we have to ultimately arrive at differential amplifier. Okay, so for that circuitry, let us see how we can modify this circuitry in order to be used as differential amplifier. The problem with this circuitry was, on the one side only you are having the load, the other side you don't have a load. So in the analysis which we done here, I have only taken this side of the circuit, and I have ignored this side of the circuit because its current was simply doing nothing. It was just going to ground. Okay, so it was not doing anything, the current. Instead of this current, instead of wasting this current, if we can utilize the current present here for amplification purposes, then we may get a good amplification and we may end up with a what is called as a differential amplifier. Okay, so for doing that, what you can do is, just instead of connecting this to VDD, you can copy this current here, this variation, whatever are coming here, you can copy that variation to this circuitry, and we know how to copy that variations. We have current mirror. So if you can replace one transistor like this, then the variations which are happening here, okay, so because of GM variations earlier, this branch was facing a GM into V in by 2 variations, whereas this branch was also facing GM into V in by 2 current variations were getting, but this current was not used to multiply with resistor, it was simply going to ground. That was the problem. So instead of sending this to ground, if we can just transfer that variation here to this branch with appropriate polarity, then both these currents can get added and we get twice the effect, okay, or twice the gain. Okay, so instead of wasting that current, if you would like to use that current, then you can use a copy circuitry here. And how to use a copy circuitry, we have just now seen current mirrors. You can simply use a MOSFET with drain and gate shorted. Okay. So now what happens? This circuit, how it works is, uh, let us say V in is very small. V in is very okay. Our voltage at this node is negative, more negative when it has become minus infinity, and voltage at this end is somewhere at positive infinity. Then what is going to happen is, when the voltage here is going to be minus infinity, what will happen to this transistor? If you are applying less than 0, you are applying, what will happen to this transistor?
Off.
Off, sir.
This transistor becomes off. If this transistor becomes off, can any current flow here? Will there be any current flow?
No.
No, sir. No, sir.
There is no current flow here. Okay. Once there is no current flow here, okay, what happens is this current mirror tries to be alive. Any circuit, whatever you connect, if they're in feedback configuration, they will try to be alive. They will try to switch on themselves. Even if this circuit tries to switch on, it will not have sufficient VDS, okay, to make it switch on. Okay. So therefore, what happens is VDS will be 0 because there is no current flowing here. There cannot be any voltage drop here. So there will be no voltage between drain to source terminal. So that means this transistor is on, but its VDS is very much less than VGS minus VDH, which means this is not in saturation region. It goes into what is called as deep triode region. So this transistor goes into deep triode region. Okay. So if this transistor goes into deep triode region, what does it mean? Deep triode means there is no current flowing, or in other words, its VDS is almost equal to 0. So if VDS is almost equal to 0, it means that this is shorted to VDD, or in other words, the voltage here is equal to VDD. Okay. Similarly, because there is no current flowing here, and this is a current mirror circuitry. So what will be the current flowing here? If there is no current flowing in this branch, what will be the current flowing in this branch?
Sir, VDD.
No, that is voltage. I'm asking about current. If there is a 0 current flowing in this branch, what will be the current flowing in this branch?
No current.
Current produced by M4 because of copying action is going to be 0 amperes. So it is also not going to flow, no current is going to flow here. And once no current is flowing here, there will be no VDS. And if there is no VDS, again, it will be as if shorted to, it will be going to VDD. Okay, right. But here what happens is, because this M2 is connected to a very high voltage, which is almost infinity, so M2 is permanently on. Okay, so if M2 is on, what it does, it connects this terminal, it will short this terminal to ground. Okay, so you are having this transistor which is on, which is not conducting, or means there is no current flowing here. So that means this is not connected to VDD because no current flow. Whereas here you have high current flow connecting V out to ground. So in other words, V out, when your V in is going to be negative, your V out will be equal to 0 volts. It will be 0 volts. Right. Now, after some time, let us say if I apply some voltage such that V in is equal to V out, both of them equal to bias voltage. I have applied VB here and VB here. In that case, what happens? Both the transistors is going to be switched on. Okay. And half of the current of this ISS will be flowing through here, ISS by 2. And half of the current of this device will be flowing here, ISS by 2. Okay. And if ISS by 2 is flowing here, that ISS by 2, okay, let me just erase this. Yeah. So if ISS by 2 current is flowing here and ISS by 2 current is flowing here, what happens is the same ISS by 2 will flow through this transistor. And because it's a current mirror, what current mirror will try to do, it will also try to produce ISS by 2 here in this branch. So ISS by 2 is provided here, and the same ISS by 2 is flowing below also. So if the same current flows, okay, these two branches, okay, what actually is going to happen is this branch, see, this branch function is very interesting. Okay, this branch actually acts like two resistors. Okay, in order to simplify the things, it simply acts like, you can assume it to be two resistors. Okay, where sometimes this resistor, there will be a huge current flowing through here, and very small current flowing through here. Okay, if it's a small current flowing through this resistor, what do you think the resistance of this path is going to be if there is a small current flowing here? When will small current flow?
Large resistance, sir.
Large resistance. So in other words, it means its resistance is very high and this resistance is very low. Okay, that means if this is 1 mega ohm, this is going to be just 100 ohms. If this is 1 mega ohm and 100 ohm, and if one end is connected to VDD, other end is connected to ground, what do you think the voltage at this point will be? If below
VDD
resistance,
into 1 mega by 1 mega.
so this is very large, this is very small, so you can assume that complete VDD is going to be appearing here. Is it or not? There
Yes,
is going
sir.
to be very less drop here, and same complete VDD is going to appear here. Am I right or wrong?
Yes, sir.
Yeah, so V naught will be equal to VDD. In this case, V naught will be equal to VDD. Now, reverse scenario, opposite scenario, you imagine. Let us say again there are two resistors. Okay. Assume that a large current is flowing here and very small current is flowing here. Okay. So a small current is flowing through a resistor, which means its resistance is small or big.
Large resistance.
Okay. It is the same scenario, no? I have assumed the same scenario. Let me just reverse the scenario. Let me just reverse the scenario. Let us assume this is there is a small current flowing here and there is a large current flowing here. So when large current is flowing through a resistor, that means this resistor behaves as what? Its impedance is
Short.
Yeah, it is having a very less resistance. And if small current is flowing here, it means it is having a
Large resistance.
large resistance. Okay. So if there is a large resistance, assume that it is 1 mega ohm. Assume that it is 100 ohms. So if this is the scenario, what is going to be the output voltage? 100 ohms here and
Connected.
it will be complete voltage VDD will
Nearly
be
to 0,
so
0.
V naught will be shorted to
Ground.
ground. So V naught will be equal to ground. Now imagine a third scenario where you can assume two resistors, okay, where some current is flowing here, X, and the same current X is flowing through this particular end. Okay. If X is flowing here, let us assume X is again flowing here. So in that case, what will be the resistance of these two things?
Half of VDD.
Same thing. Okay. It is going
Same.
to be whatever equivalent by 2 or RE by 2. And what is going to be V naught?
VDD by 2.
VDD.
Half of some.
Half of that thing. Okay. So it is going to behave in the same way. Okay. So here, because of this current mirror, what current mirror is trying to do is, it is trying to create a difference in current in this path and in this path. The current in this path is decided by this transistor, whereas current in this path is decided by this transistor, which in turn is decided by, which in turn is dependent on this transistor, and which in turn is dependent on this transistor. Okay, so the current in this path, I can say, is decided by your this transistor, whereas current in this path is decided by the second transistor. So M1 and M2 are deciding the current. Okay. So what is happening here? In the earlier case, we have assumed M1 was V in was very small. So when V in was very small, there was no current flowing here and no current flowing here, and there was large current flowing here. So we were actually in this scenario. Okay. So above circuit was producing small current, below circuit was producing large current. So our output was equal to in this case what?
0, 0.
Ground.
here. So it was when V input is negative, output you will get it as 0. When both of them are same, let us say V in by 2, here I apply same bias voltage VDD by 2, VDD by 2, what will happen? Same current will be drawn by this transistor and same current will be produced by this transistor, which again through current mirror will be produced here. So what is going to be the V out in that case? If same current is flowing, our circuit is going to be
VDD by
in the
2.
third scenario. Okay, in third
VDD by
scenario, what
2.
is the output voltage?
VDD by
by
2.
2.
VDD by 2. Actually, it will not be VDD by 2. It will be some bias voltage. Okay, it will be some bias voltage. And let us assume we will see that why it is not VDD. The reason why it is not VDD by 2 is because one end is connected to VDD, other end we are, in this case we are connecting it to ground, but you can see other end is not connected to ground. There is another transistor present here. Okay, so because of that I am saying it is not VDD by 2, it will be something else. Okay, we will come back to that point later. Okay, first we will understand the working. Now what happens when I increase a positive voltage here? Well, let us say if I apply positive infinity to V in and a negative infinity to this transistor. If negative infinity is applied, what happens? Will this transistor will be on or off?
Off, sir.
It will be off. That means a small current will be flowing through this branch. And you have applied a positive infinity to this transistor. So what will be the current flowing here? Huge
Infinity,
current
sir.
or large current
Large
will be
current.
flowing here, which through current mirror will be reflected here also. So that means the upper part of the circuit will be producing large current, whereas below part of the circuit will be producing small current. This is similar to the first scenario. You can see here this scenario: upper circuit producing large current, below circuit producing small current. So in this case, your V out will be
VDD.
VDD. So V naught will go to VDD. So that is what will be the characteristics of your uh, this differential amplifier with current mirror load. This circuit, whatever is written here, is drawn here. It is given the name as differential amplifier with active current mirror load. Okay, so their operation is going to be different. They are not going to behave like differential amplifier with a resistive load. There the difference in vout1 minus vout2 was because of voltage drop in resistors. Here there are no resistors, it is the current mirrors. So current mirror, by producing different amount of current in different branches, okay, in different part of the branch, it is trying to change the output. Okay, so that is how operation here differs. So as you can see here, so this is the characteristic, last signal characteristic which we have drawn. Okay, so when V in minus V in is negative, V in 1 minus V in 2, or in other words, I've taken it as V in only. When it is negative, you are getting output as 0. When it becomes positive, you are getting output as high. Right. This circuit now has lot of limitations. Okay, so what are the different limitations here? The first limitation is what is the bias voltage you have applied here. Okay, so there is a limitation on that, how much you should go, how much you should. I cannot go and apply 5 volt here or 0 volt here. Okay, there is some range from 0 to some xyz. I should apply only within that. So if 5 volt and 0 is here, if this is the scale, there will be on some portion of the scale where I will be able to apply this. There are some conditions for that. Input, you know, our input, whatever we apply, can this circuit or can this amplifier amplify this input? Okay, if the input is coming at 0 volts, will it be able to amplify? Let us say the signal is very small, 10 milliamperes is the 10 millivolt is the amplitude of the signal. Okay, and it is varying along 0. Will the circuit be able to amplify the signal varying along 0?
Sir, maybe, sir. Maybe, sir.
Maybe.
No, sir.
Why no? Why no?
Should be average. Why should it should be average in active region?
I am unable to get you properly.
I think the waveform should be along y-axis, means
Yes.
parallel to above x-axis. Then
Right. That is what you need to attach some amount of, what is that? This is a pure AC signal.
Offset.
Offset.
Yes.
Pure AC signal, if you apply here, it will not be able to cross threshold voltage. If it is not crossing threshold voltage, will this transistor will be in saturation? It will not be in saturation. Therefore, it will not be able to amplify that signal. So therefore, if you want the signal to be amplified, you need to add what? You need to add offset, or in other words, DC bias to your signal. What you should add? What you should add?
Bias, bias
Bias.
DC
voltage.
bias.
Signal should be amplified at some voltage. Okay, some voltage, it should be shift, some DC voltage should be added to it so that it shifts up and it becomes completely positive, and the transistor will be in saturation, will be able to amplify that. Okay, now the question is, what should be this voltage? What should be the bias voltage which you are adding to the input signal? See, this signal, this DC, whatever I have said you earlier, right? So directly if you give this
Greater than
signal,
VTH.
it is
Greater than VTH.
greater than
We should
VDS.
choose. We should choose using DC offset. Means DC characteristics we need to from the DC
Right.
characteristics table.
Right. But in the exam, they will not give you cadence. In exam, you need to theory, formulas, okay? Right. So here, what you will do is, we know every signal, if it's an AC signal, directly it cannot be amplified. We need to add some offset or DC to it in order to make a signal which is like this. So the AC which you are adding in differential amplifier, not in what do you say, single stage amplifier, we add DC in single stage amplifier also. But in differential amplifier, the DC what you are adding, it is usually called as, it is given a name more commonly, it is called as common mode signal. Common mode signal. And the actual signal is actually called as differential signal. Differential signal. Okay. So here, what do you say, differential signal, directly if you apply at 0, it will not be amplified. So you need to add some common mode signal to this particular differential signal. Now the question is, what should be that common mode value? Okay. And will it be a single value or a range of values? Can anyone say me, will it be a single value or a range of values?
Range of values.
It will be a range of values, because we know in the characteristics, wherever this curve is, wherever you have a curve which is very much steep, okay, so it will be steep not in at a single variable, but there will be a range of inputs for which it is going to be steep. So that is going to decide. So that input common, what do you say, the range, that means I can have an input signal which is a DC bias, or I can have an input signal which can be a DC bias. So both of them will be amplified. So this common mode range, the range for which you can vary the common mode signal such that it gets amplified by the same amount. Okay, you call that range as input common mode range. It is also called as ICMR, input common mode range. Okay, and this is one of the very important criteria that you should use while designing the differential amplifier, input common mode range. Now there is one more limitation. What is the other limitation is this V out signal. Can you say me what will be the V out signal looking like? Will it be like this? Will my V out be a completely AC signal like this? You have done simulations. Will you get V out which is like this?
Yes, sir.
Huh? Yes.
Yes, sir. DC will be null.
DC will be 0.
Actually, it should be 0. Maybe some small amount will, some distraction may come.
It will not be 0 unless and
It
until
will be
you
along
subtract
same
it.
offset. Okay.
Until you subtract it. In the earlier case, you were subtracting it, there you were getting 0. But here you can see there is no 2 outputs, only one output is there. So there is no subtraction here. So what is going to happen here is you will get output with the DC. Amplified signal will also contain a DC. Okay. Or in other words, this swing, output swing, there is something called as output swing. The signal will be having an output swing, which again have limits. You will have a maximum limit and a minimum limit to this particular swing, output swing. Okay, so even that is one more limit you need to take out. So therefore the output will have an output swing range. Okay, that also you need to take into account. So there are three limitations which you need to take into account. One is the bias voltage which you apply here. Second is the input common mode range which you are applying to the signal. And the third is the output swing which you are getting at this particular output node. Okay, now let us just try to find out what are the values or what are the limits on that. We will first start with the output swing limits. Okay, so what do you think will be the output limit here? Yeah, so the maximum you can see, the maximum value which you can get here, actually you would like it to be VDD, but again if the value goes to VDD, the problem what happens is this transistor which is present here will go into triode region. Okay, once it is in triode region, you know you will get distortions. Our amplifiers characteristics we have seen, it will be like this. Once the transistor enters into triode region, the curve will bend and you will have distortions. Okay, so if you don't want distortions, then what you are supposed to do, you have to maintain this transistor in saturation region. That is the only thing you can do if you don't want distortions. So therefore, if you don't want distortion, then the voltage, this transistor should be in saturation, and when a transistor is in saturation, its VDS will be equal to VD sat, and with that VD sat will be given by the equation you would be knowing it. It is 2ID by mu n C ox W by L. In this case, W by L of 4. Okay, so this is what is the saturation voltage of VD sat. So you should maintain this much difference across the VD sat such that it doesn't go into triode region and doesn't distort the waveform or output waveform. Okay, so such that it, in other words, such that it remains in saturation. So therefore, the maximum voltage which you can go at this point without affecting this transistor, without making this transistor go into triode region, is VDD minus VD sat of 4, which is nothing but VDD minus this equation, whatever I have written here, VDD minus that. That is the upper limit. Okay, that is the upper limit which you can go. Okay, starting from 0, if this is my VDD, so the maximum limit at which you can go is VDD minus VD sat. What is the lower limit which lower voltage which you can have at this point? Okay, so the least voltage here should be such that this transistor and this transistor, both of them should be in saturation. Okay, so the least voltage, the minimum voltage which you can have here is equal to the saturation voltage of this transistor or saturation voltage of this transistor. If you go below that, either this or this transistor will go into triode region, and if one of the transistor goes into triode region, you will get distortions in the output. So we don't want distortions. So therefore, the minimum voltage which you can go, minimum swing which you can have, is equal to the saturation voltage of this transistor, which is VD sat 5, plus saturation voltage of this transistor, which is VD sat 2. So that is the minimum voltage, which is equal to 2 overdrive. This saturation voltage is also called as overdrive voltage. Okay, so it is equal to 2 overdrive of 2 transistors. So it is VD sat 2 plus VD sat 5. So this is the limit of your output swing. Okay, so your output swing is limited by 1 overdrive on the top and 2 overdrives below, and this is the maximum value. Worst case values will be this is actually the best values which you are going to get, but as per your design, it may be far more lesser. Your range might be far more lesser than what is written here. This is the best value or the best range which you can get from this circuit. Is it okay? Now let us now try to understand what is the limitations you have with respect to input. Yeah, with respect to common mode, what is the limitations you have? Let me just make a copy of this. Yeah, so your input DC, whatever you are applying, common mode means what? Wherever your AC signal is coming, it should, the DC associated along with that, you are calling it as common range. Okay, so this is minimum ICMR, input common mode range minimum, and input common range maximum ICMR max. Okay, so what is the limited minimum limit which you can have? We will start with the minimum limit. So the minimum DC voltage, it is nothing but a DC voltage. So the minimum V in CM minimum will be such that, again, this transistor should be saturation and this transistor also should be in saturation. Okay, so in other words, here this voltage drop from here to here is going to be VD sat 5, and it should be this voltage, because you're applying to gate, it comes under the category of VGS 2. Okay, so your V in CM is equal to VGS 2 plus VD sat 5. Okay, but we know for this VGS2, this voltage, whatever you are applying here, okay, it should be greater than its threshold voltage. Okay, so this VGS should be greater than its threshold voltage. Okay, so therefore you will be having the input CM, V in CM. So the minimum value which you can have for VGS2 is the threshold voltage. Okay, the minimum value is threshold voltage. So therefore you have VD, VGS, okay, VTH, okay, RL1 VG, you have threshold voltage plus VD sat 5. Just by having threshold voltage, it is not enough for you. Okay, if I let us say threshold voltage of this device is 0.5 and I am applying a common mode voltage of 0.5, okay, so that is going to just turn on the device. Okay, just turning on the device is not enough. Your device should be at bias point. It should be able to consume, it should be able to, what current should flow from here at the bias point? What current will flow here at bias point? You have left the meeting. Are you there?
Sir.
Yes, sir.
Sir,
Ah,
yes, sir.
what current will be flowing through this M2 transistor in bias at bias point? If the total current flowing
By
here is I5, what current should flow here at bias?
Zero, sir.
Zero.
Zero, sir.
No, at biasing. In
I5 by 2, sir.
I5 by 2, half of the current at bias point, half of the current should flow from here, half of the current should flow from here. Okay. So if you apply a voltage which is equal to threshold voltage, you are just turning on the device. You are not making I5 by 2 to flow through this. Okay. So turning on the device is different. Making I5 by 2 to flow from there is different. Okay. So you have just turned on the device. If you want I5 by 2 to flow from there, you need to add some extra voltage to this input voltage. You need to add some extra voltage. What is that extra voltage? That extra voltage is going to be your VD sat 5. We know in your saturation, if you want this device to be in saturation for I5 by 2, then VDS of second transistor should be greater than its VGS minus VTH. Or in other words, greater than or equal to, if I take the boundary condition, it is equal to VGS2 minus VTH. Okay, or in other words, VGS2 should be equal to VDS2 plus VTH. It should not only be threshold voltage, this extra thing what is getting added there is its VDS. And VDS of what? VDS of saturation. VDS of saturation at ID equal to I5 by 2. When I5 by 2, if you are expecting I5 by 2 to current to flow there, then whatever is the saturation overdrive you require, that thing should be added here. And how will I get this VD sat? You know, again, you have an equation under root of 2 ID 5 by 2 divided by, or else under root of 2 ID divided by mu and COX W by L of second transistor. This is going to give you the VD sat of second transistor. and that needs to be added. So that is the minimum. So V in minimum or V common mode minimum will be saturation voltage plus threshold voltage plus extra voltage that needs to be added for this condition to be satisfied. Overdrive for it to go into saturation, which is going to depend on VDS2, which is nothing but overdrive. Okay, so VD min is equal to VD sat of 5 plus VD sat of 2 plus VTH of 2. Okay, so in other words, it is equal to 2 times overdrive voltage and 1 time threshold voltage. Overdrive voltage can be as minimum as 0.1. So you can have 0.1 plus 0.1, but threshold voltage will be somewhere around 0.5 to 0.6. So that means the minimum voltage which you can apply, which you have to apply along with the input, is around 0.7. This is just an example. Don't take it too seriously. Okay. Right. So this is the minimum voltage you can go. You should not go below that. So ICMR here minimum, it is decided by, this value is decided by VD sat 5 plus VD sat 2 plus VTH of 2. This is the minimum voltage. Similarly, what is the maximum voltage which you can apply here? The maximum voltage which I apply here, okay, maximum voltage whatever I am going to apply here, it should be such that this transistor is in saturation. Okay, and for this transistor to be in saturation, it is actually going to depend on your Vout. Okay, so what is the VDS voltage here? Let us say this end is P and this is Vout. So VDS of second transistor, VDS max of second transistor is going to be Vout minus VP. Okay, and for this transistor M2 to be in saturation, its VDS should be greater than VGS minus VTH. So therefore, V0 minus VP should be greater than or equal to, what is the maximum voltage you are applying? So V in max minus VTH. Okay, V in max minus VTH minus VP. With respect to VP, I am applying. Okay, so here you can cancel or else VP, I'll remove it here. So therefore, I will take the boundary condition, that is V0 minus VP is equal to V in max minus VTH. So it gives me V in max is V0 minus VP plus VTH. Okay, so this is the maximum voltage I can apply at inputs common mode. So it is equal to V0 minus VP plus VTH. This is the range of input. And what is the VB you will be applying here? You have seen the limits on input, you have seen the limits on output. Now let us see the limit on biasing point. So this bias voltage is well defined. It should be equal to VD sat of 5. Okay, so your VB minus VTH, VB minus VTH should be less than or equal to VD sat 5. Or in other words, VB minus VTH of 5, fifth transistor we are talking about, should be equal to, what is VD sat of 5? It is under root of 2 ID5 divided by UN COX W by L of 5. So VB should be equal to under root of 2 ID5 by mu n COX W by L of 5 plus VTH of 5. Okay, so this is the condition for VB. So if you satisfy all three conditions, then you will be able to use this transistor as what do you say, differential amplifier. Okay, and one important thing which I've missed to address about this amplifier is this amplifier doesn't have two outputs, unlike the earlier amplifier which we have seen, where there were two resistors and two transistors we have taken here, right? So it is there you were getting two output, V0 plus and V0 minus. Okay, here unlike that, this is going to have only a single output, which is here. Okay, so this transistor is also called as differential input single-ended output. Differential input single-ended output amplifier. So this was all about the large signal analysis of this amplifier. If you want to see the small signal gain, what is going to be the small signal gain, not common mode. small signal gain of this amplifier, if I try to analyze, current mirror load, okay, small signal gain. This amplifier is actually similar to this amplifier, which we have seen here. Okay, earlier we have done an analysis, right? Yeah, this amplifier. But the only thing is here, instead of having the load here, you also have a load in this path. Okay, so that means instead of having only one current affecting, you now have two currents affecting here. The second path also is affecting. So the GM of this transistor, so the GM of this transistor based on analogy of previous circuit, its GM is going to be 2 times the GM of previous circuit. Okay, so which is going to be 2 into minus GM by 2, which means its amplifier, okay, not minus GM, it is going to now have a plus GM. Okay, because the characteristics, if you see earlier, when V in is becoming positive, the output is becoming positive. When V in is becoming negative, output is becoming negative. So it actually has a positive GM. Okay, so it is, the original circuit was GM by 2, now it is multiplied by 2, so you will get a GM of 2 for this particular circuitry. And what will be its output impedance? You can see its output impedance. When you see it from this end, you will have one transistor and the other transistor connected here. So it is as if you're having, okay, so you can assume this transistor to be a transistor with a fixed bias. So its impedance will be equal to RO, or its channel length modulation impedance RO4. This also you can think it to be a fixed bias, because in small signal we will ground small signal, but you know the small signal is associated with the bias voltage also. So if you can treat that bias voltage, it actually acts like a current source. So it also acts like a resistor RO4. Okay, and this node P we have seen earlier in the earlier differential analysis that you can actually ground this node P based on half circuit analogy, based on half circuit concept. This P can be grounded. So once you can ground this P and consider only the half circuit present on left side, so on V out you have on top a resistor RO4 connected to ground. Below you have another resistance RO2 connected to ground. So when you see it from this side, R out will be simply equal to parallel combination of RO2 and RO4. So therefore you have R out, you have GM. The gain of this circuit is simply GM into RO2 in parallel with RO4. This is the small signal gain of differential amplifier with current mirror load. Okay, so the circuit which you are seeing here, okay, this is also called as a single stage op amp. The differential circuit which you are seeing here, the another name of this circuit is, it is also called as single stage op amp. Okay, so when we begin our unit 5, okay, which we will be doing in next class, we will be starting with the same analysis, same thing we are going to repeat. Okay, so as it is same thing, I may not repeat, I may skip that. I will only concentrate on the other things which are not repeated here. Okay, like for example, for this to act like an op amp, the output should not be, you should connect a capacitor at the output as a load, not a resistor as a load. Okay, that thing we will discuss in next class. So this circuit which you are seeing here is also called as single stage op amp. We will see the design procedures and all in the next class. We will end our class here. Yeah, at this point I would like to ask about the assignment 1 which you have not submitted. Why you have not submitted?
Sir, you said you will give another assignment, sir. Actually, you didn't give yet.
I did not give.
No,
I
sir.
have given, I think I have given one question there.
You said before one assignment, sir, about capacitances, that thing.
Hmm.
But another time you said you will give another assignment instead of that, sir.
Okay.
We are waiting for that.
As of now, what we will do is, do you have access to this? What is this? Your portal. Do you have access to the portal?
LMS, sir.
LMS.
Yes, sir.
Are you able to see my subject there?
No, sir.
You're not able to see.
No, sir. Any subjects? We can't see any.
See here, in that, what we will do is there will be an option for quiz there. In that portal, there is an option to take a quiz. So what I will do is I will post the assignment questions there tonight. Both the assignment 1 and 2. 2 also you are supposed to do here. We are almost at the end. So both assignment 1 and 2 questions I will post there, and one slip test also I will plan, which we will have it at the last class. Okay, whatever is our last class, or whatever is the free period you have at that time, I will schedule that slip test. So based on these three, you will be awarded the marks. Okay, so you are not able to see my class means I think the programmer has not enrolled you uh, under my course. Okay, I will call him and ask him to enroll you under my course. Once you are enrolled, you will be able to see my this thing, my lecture notes and videos also. You will find it on the LMS portal. I am uploading that. I am in the process of uploading that. Some of them I have already uploaded. Okay. Once so all the videos you'll be able to find that, and PPTs whatever I have used, the PDF of that you will be able to find there, and the remaining slip test and assignment questions also you will find there. Is it okay? I will share the
Okay,
assignment
sir.
question because you are not enrolled till now. So the assignment questions I will share by tonight. By tonight 10 o'clock, I will put it in your mail, your group mail, whatever is there. Assignment 1 and 2. You try to do that and be ready. Submission will be through LMS portal. You will be submitting through LMS portal. Is it okay?
Yes, sir.
Okay. Right. Thank you. You can give your attendance in the chat box. Yeah, I'm ending the meeting now. Thank you.
Thank you, sir.